Okay, good morning. That was really sad. Good morning. Much better, thanks. So how was the exam? Oh, 2 thumbs up, good. Okay. All right, so I'm going to send in the Scantrons today, and the data processing people will process them. Expect to get the results back sometime in the middle of next week is what I think is a good, reasonable expectation. Okay? All right, today we're going to start a new chapter, chapter 11. We're going to talk about sequences. And eventually we're going to talk about series, which is related to sequences, but a lot harder than sequences. We'll start easy with just sequences. So a sequence is nothing more than a list of numbers in a specific order. Right? So that's nothing more than, that's what a sequence is, just a list of numbers in a specific order. Some examples that we're familiar with. All the even numbers. Right? So we write sequence by putting the numbers between 2 curly brackets. So all the even numbers we all know are 2, 4, 6, 8, 10, and we can go on forever. Okay, so this is what's called an infinite sequence. Because there's no end to it. There's no end to the even numbers, right? Whatever even number you can give me, I can find another one bigger than that by simply adding 2 to it. So there's absolutely no end to it. Another one that some of you might have seen before, the book talks about this. It's called the Fibonacci series. A sequence, sorry. The Fibonacci sequence, it's named after an Italian mathematician whose pen name or nickname was Fibonacci. His real name was actually Leonardo of Pisa. Not pizza. All right? Okay, so how many people have seen this Fibonacci sequence before? Good. So it's a very interesting series. We start with a 1, and then anything that comes after that is the sum of 2 previous numbers. So the next one, of course, is 1. Well, you're adding 1 to nothing, right? Then the next one is going to be 1 plus 1, giving you a 2. And then next one, 2 plus 1, a 3. And then the next one would be a 5, 8, and then 13, and so on. Right? So each one is the sum of the 2 previous terms. Each number is called a term. Let's talk about notation. Often you'll see sequences given like these, bunch of numbers between 2 curly brackets. Now sometimes you'll see this kind of notation too. A sub n between 2 curly brackets. So this is just saying that we have some sequence that I don't want to write all of them out. So there's my something to denote all of these things potentially. It's exactly like you would write f of x instead of a function all the way out, right? Just a shorthand notation. Sometimes more explicitly like this. So saying that we start with the first term, a sub 1. So in the example above, this will be a sub 1, the first term. This will be a sub 2, and that's a sub 3, and so on. Somewhere down there, there's an a sub n. Okay? Another way we can give you sequence is to tell you how these sequences come, how these numbers are derived. So for example, here's another way to write a very specific sequence. Okay, so this tells you how to come up with these terms. We always start at n equal to 1. So the first one is n is equal to 1. And if I put 1 into here for n, I get 1 over 1, right? So that's a 1. And then I move on to n is equal to 2. And I get 1 over 3. And then I do n is equal to 3, and so on. So let's see what do we get. We get 1 over 5. Right, you get the idea, right? You putting a new n, each one is 1 bigger than the previous one to come up with all of these numbers. So the next one, what would this be? 1 over 7? 1 over 9, and so on. Okay, so these are different ways that we can tell you how to write out a sequence. Questions? Good? Good. So let's write a few terms of this sequence right here. So here I'm telling you what an is. Each term is derived this way. Okay, so take 30 seconds and write out 5 terms of this thing. Remember, you start with n is equal to 1, and then n is equal to 2, and so on and so on. So, how about 3 terms? Because 4 to the 5th is an awfully large number. Stop it. Okay, better. All right, got these? What's the first one? Right. Next. Yep, and then, yeah, exactly. The next one, 1 over 256, and so on, right? Okay, so you get the idea. You're just plugging an n for each one, and then you get a bunch of numbers out. How about this one? Okay, do you remember what this exclamation mark factorial means? Raise your hand if you know what it means. Okay, so for those of you that forgot what this is the factorial symbol. It's not a very excited number. It's just factorial. So, for example, 3 factorial means 3 times 2 times 1, and 4 factorial means 4 times 3 times 2 times 1. Okay? All right, so again, write out a few terms of this thing. I don't know, 4 terms. First term is 1 factorial, which is 1 times 1, so 1, over 2 factorial, so 2 times 1, right? And then 2 factorial, or rather, let's write this out. 2 times 1, and then 3 times 2 times 1, and then 3 times 2 times 1 over 4, 3, 2, 1. Right? And this simplifies to 1 over 2, 1 over 3, 1 over 4. Okay, now we see a pattern here. This is a very important thing that you should be able to do with sequences and later with series. Often after you write a few terms, 3, 4, or even 5 terms, you start noticing a pattern. 1 over 2, 1 over 3, and 1 over 4. So in this case, the pattern is pretty clear. I no longer need to go back to that. I can predict what the next one is going to be, and the next one, and the next one. Right? Questions? Okay, now let's reverse the direction of that. So I started out by giving you the compact form, telling you how to get these numbers. Let's reverse that. So let's take the series we just, not a series, the sequence we just had. Write in the compact notation. Well, of course, one way to do that is we just saw. Right? We know this gave us that, so of course that's one way to do it. Now here's an important question. Is that the only way to do it? No. In fact, if I give you this sequence here and tell you to write me a formula, you probably wouldn't do that, right? Because the pattern here is so simple, I probably wouldn't think of something that complicated. So what's another way to describe the sequence we see above? 1 over n plus 1. Yeah, excellent. Okay? So that's an important point here. If we go from a list of numbers to an, the answer is not unique. Right? I have at least 2 ways to go from here to the an notation. Can you think of another way to do it? Probably, but we found an easy way to do it. That's often the thing we're looking for. But that's an important point I wanted to make, that it's not unique. Another way that sequences can be described is by giving what's called a recurrence relation. For example, here's a new sequence here. I'll tell you that the first term is 6. And I'll tell you that the term after any nth term is given by whatever the nth term is, divided by n. So this thing right here, this is what's called a recurrence relation. Once you tell me one of them, I can tell you how to find the next one, the next one, the next one by repeatedly using the same relation. But you see, the difference between this and that is I have to know at least one term to start, because this depends on the previous one. This one, we could just start counting n is equal to 1, 2, 3 until we say enough, right? Okay, so let's write out a few terms here. First one is, of course, 6. Right? So this is given. I don't need to do anything. N is equal to 2. We would take, so think of that as n, a of 1 plus 1 in that notation. Right? So a of 1 plus 1 is equal to a1 over 1. So that's a 6. N is equal to 3 is the next one. And I would get that by taking a2 over 2. Right? So I get a 3. Now what's the next one? The next one is a4, so we use n is equal to 3. So what do we get? According to the recurrence relation, it is a3 over 3. And a3 is 3, so 3 over 3 is a 1. Does that make sense? How recurrence relation works? You take the previous one and then get the next one by using the formula given here. Any question on this? No? Okay, good. Now let's talk about what we can do with sequences. And first we'll start with a very important property of sequence and later series too. They're very closely related things. So many of the things that we do with sequences, we can do with series. A sequence AN here converges, or another way to say that is that it is convergent if it has a limit. Limit n goes to infinity, a n, and we'll call the limit L. So if you get the limit out of it, meaning you get just an ordinary number, not infinity, not minus infinity, does not exist, then we say the sequence converges. If that doesn't happen, then the sequence diverges or is divergent. Okay? This thing can only be convergent or divergent. There's no somewhere in between. There are no shades of convergence here. It's either converge or not. Now be very careful with this word convergent. This word means different things in different contexts. So here, it means that we have a limit. But later on, we're going to talk about the convergence of series. That means slightly different things. So just be very careful. In the context of just sequences here, this means this very, very specific thing. But it is not necessarily the same when used in a different situation. Okay, so let's take a look at what happens here. Suppose I have this sequence. Let's write out a few terms here so we know what we're looking at. When n is equal to 1, minus 1 to the 0th power, that's a 1, right? 1 over 2. When n is equal to 2, we get negative 1 over 3. N is equal to 3. N is equal to 4, sorry. And then n is equal to 5, and so on. Okay? If I take a limit of this thing here, let n go to infinity. What do I get? What's the numerator doing? It's just flipping signs, right? Just doing its flipping sign thing. It doesn't do anything interesting. The denominator is getting bigger. So when I take n to be a very large number, what will this eventually end up being? Yeah, the limit will eventually get close to 0. We'll never get there, right? We can never get to exactly equal to 0, but we can get so close to it that practically it's at 0. So this tells me one thing. First of all, the limit, or rather the sequence, converges. And graphically, what this number is telling me, try plotting these things. So these are the n's. When n is equal to 1, we get 1/2. I'll put it up here. When n is equal to 2, we get negative 1/3, down here somewhere. And then when n is equal to 3, I get 1/4. And then minus 1 over 5, 1 over 6. Okay, so the pattern here, do you see a pattern here? What are they doing? What are these dots doing? They are going to 0. See? Now you see why we call this thing convergent. They're converging onto something. Right? They're converging onto something. And that something is what you would get by taking the limit. Does that make sense? Yep. Let's look at a divergent sequence and see what the dots are doing. We'll make it very simple. How about just n? So this is 1, 2, 3, 4, 5, 6. Let's stop here. Okay. And when I take the limit as n goes to infinity of n, of course I get infinity. So the limit I get out of it is not an ordinary number. I get infinity or minus infinity. Either way, it's not a number I can do anything with. So that's a divergent sequence. And if you were to graph it, this looks pretty easy actually. 1, 2, 3, 4. 1, 2, 3, 4. When n is equal to 1, n is equal to 2, 3, 4, 5, 6, and so on. Right? So these dots are not going anywhere in particular. They're not converging onto any horizontal line. So that's a divergent kind of thing. One more example before we talk about, oh, actually 2 more examples. Okay, take 2 minutes and find out if this thing is convergent. Let me give you a hint. Don't take the limit letting n go to infinity right away. Think about the definition of factorial and simplify this before you take the limit. Okay, so does this thing converge? Raise your hand if you think yes. Okay. Let's find out why or why not. Okay, remember I said we got to use the definition of factorial. So when you have something factorial means something times something minus 1. I should have used something shorter than something. Minus 2 and so on, right? You get the idea. So upstairs, this is 2n minus 1 times 1 less than that, 2n minus 2, 1 less than that, 2n minus 3, 1 less than that, 2n minus 4, and so on. Right? Downstairs is 2n plus 1, 2n, 2n minus 1, 2n minus 2, 2n minus 3, 2n minus 4, dot, dot, dot. That's a 4. Right? And then you see a bunch of things cancel, right? 2n minus 1, this goes away. 2n minus 2 goes away. 2n minus 3 goes away. 2n minus 4 goes away. Dot, dot, dots go away. Because whatever this is here, it's the same as that. Right? It's very clear that these dots and those dots are exactly the same. So this ends up being 1 over 2n plus 1 over 2n. And very clearly that if I take the limit, I get a 0, right? I get a 0 out of that. When I take the limit, it's an ordinary number. It's not infinity. It's not minus infinity. So yes, it does converge. Make sense? Question? Okay, let's do one more. Find out if this thing is convergent. E to the power of 3 over, n to the power of 3 over e to the power of negative 2n. I think you can do this very quickly. I'll give you 1 minute. Okay, raise your hand if you think it's convergent. Fewer hands now. Raise your hand if you think it's divergent. Did everybody raise a hand? You can't be somewhere in the middle. You can't be kind of divergent. You gotta be divergent or convergent. Okay, let's find out what's going on. So this is n cubed over e to the 2n, right? So when I take the limit, when n goes to infinity, obviously that blows up. That also blows up. What do you do when this happens? Calc 1. L'Hopital's rule. That's one way to do it. Yep. So how does that work? How does L'Hopital's rule work? Take the derivative. Yep. So I'm going to write an L here to denote I use L'Hopital's rule. So I take the limit. I get 3n squared over 2e to the 2n. Then I try again. still going to that thing. Then I do it again, right? I do it until it stops doing that. 6n, 4e to the 2n. Okay, one more time. 6 over 8e to the 2n. Aha. Now it's not doing this anymore. And when n goes to infinity, 6 is 6. E to the 2n blows up. So this goes to 0. Okay? So this converges. So another way to think about convergence is that these terms are getting smaller and smaller, and eventually they settle around something. Questions on this one? You remember L'Hopital's rule? Yep. How can you forget? Who's L'Hopital? Some guy. Okay, now let's talk about two more things about these sequences. We say that a sequence is increasing if for all n greater than or equal to 1, a n plus 1 is bigger, strictly bigger than a n. A sequence is decreasing. Same thing, if for all n greater than or equal to 1, a n plus 1 is less than a n. So what it's saying is that it's an increasing series if the terms keep getting bigger. If you look at any two neighboring terms, the one after is always bigger. So give me an example of a sequence that's increasing. A sub n, yeah. How about 1, 2, 3, 4, 5, right? That's clearly an increasing sequence because I pick any random term here. It's bigger than the one before it, bigger than the one before it, so on and so on. How about Fibonacci sequence? Is that increasing? Yeah. We're adding stuff, right? And obviously it's an increasing. A decreasing sequence, 1 over n. Isn't that a good one? 1 over n, right? So that's clearly a decreasing sequence. Each term is smaller than the one before it. So I pick any, give me any n is equal to 2, for example. A3 is smaller than A2. Give me another n is equal to 6,825. I can be pretty certain that this will still be true. Yep. A sequence is not monotonic if it sometimes increases and sometimes decreases. Or sometimes ends up being equal. So for example, if I take this one right here, just n, it's right now increasing sequence. But if I change that 3 to a 2, right? Notice that we stop increasing at some point. So that makes this sequence a sequence that is not monotonic. When it's not monotonic, there's no point in talking whether it's increasing or decreasing. It simply isn't. Yeah. That's right. Yeah, at some point, right, you can find somewhere that's, but if you disregard those two, then you just take subset of that, then that's an increasing sequence. Yeah, good question. Okay, does that make sense what these things mean? All right, so now let's take a few sequences and find out if they are increasing or decreasing or not monotonic. I'll show you two ways to find out if this is increasing, decreasing, or not monotonic. Let's look at this one, 1 over 2n plus 3. So if this is an, then an plus 1 is equal to 1 over 2 times an plus 1 plus 3. Right? I simply change every n I see on the right side to n plus 1. So that turns into this. So this will be 2n plus 5. And now we need to know if an plus 1 is bigger or, let's say, smaller than an for all n greater than or equal to 1. What do you think? One thing you could do is to always write out a few terms. This is another good practice with series later on. If you get confused about series, write out a few terms. And like I said before, hopefully you'll notice some pattern that it will continue. So let's check out a few terms here. N is equal to 1, I get 1 over 5. N is equal to 2, I get 1 over 7. N is equal to 3, I get 1 over 9. N is equal to 4, I get 11. N is equal okay. A pattern emerges, right? You see, this, when you get confused about stuff like that, write out a few terms. Very often you're going to see a pattern that shows up right away. And that can often answer the question. So what do you think? Is this a decreasing, increasing, or not monotonic sequence? Decreasing, very, very clearly. So yes. Okay? Now here's another way of doing that. If you don't like to play with numbers and reason that way, there's a more algorithmic way to do it. Sometimes when you get a complicated one, it may be a little difficult to do this. So this is a good way to also know. So for this one here, we want to imagine that an are points from some function, f of x. So what I mean is that if you graph these points, 1 over 5, 1 over 7, 1 over 9, 1 over 11, 1 over 13. We're going to imagine that these are actually points from some function like this. Right? So at at very even, very regular intervals, I sample that function, and I grab a point, grab a number, and then put it here. I sample it again, put it here, sample it, put it here. That's how I got my sequence. That's one way to think about it. Now, to determine if that sequence is increasing or decreasing, we simply have to find out whether the function is increasing or decreasing. If this function is a strictly decreasing function, then my sequence is also a decreasing sequence. So if f of x is increasing or slash decreasing, then an is the same, right? Increasing or decreasing. Does that make sense, the reasoning behind this? Yes? So for this one here, what do you think the function, let me write out an again. What do you think that function in red we saw on the last page would be? How about that one? Right? That's the same thing. If I restrict myself to x being integers, then automatically I get all the points for my sequence. But if I think about this function actually is a smooth line, a curve like the red one we saw earlier, then f of x is equal to 2x plus 3. That's really blurry. Then, yep, it's exactly the same thing. This is part of that. Now, how do you find out if a function is increasing or decreasing? Take the derivative. Right? That's how we determine what the function is doing. We take the derivative. And what do we get here? Minus 2 over 2x plus 3 squared. Is that it? I think. Plus 1 minus 2 times. Yep, I think that's it. Okay, now you got this thing here. What do you do with it to determine if it's increasing or decreasing? The sign, right? The sign of this will tell you what's going on. If it's plus, then it's increasing. If it's negative, then it's decreasing. For any x, of course. So look at this. For any x, 2x plus 3 squared is always positive. No doubt about it. So negative 2 over 2x plus 3 squared must be always negative, right? So this means that the function is decreasing. So sequence is also decreasing. All right, so make sure you know how to find out whether a sequence is increasing or decreasing both ways. Some sequences are hard